So, dobro jutro svima, buona dimineața. Good morning, everyone. Thank you for joining us for the second day of the Serbian Machine Learning Workshop. We hope you have found the first day as exciting as we have. It was certainly a very intense experience on our end, but we believe we managed to make it run very smoothly. I also hope you're looking forward to the second day as much as we are. We have a very exciting, diverse program of different kinds of sessions, starting from today's sponsor introduction to keynotes, interactive sessions on how to advance your machine learning career, panel discussions on the state of AI in Eastern Europe, and also a live coding session where I will try to beat the clock and build a drug discovery system from scratch in 1 hour. So if any of this sounds interesting to you, we do hope you will stick around. For now, we will kick off today with a special presentation from one of our partners, Anari AI. And it is my great pleasure to introduce Bogdan, who will be speaking to us about Anari, which is one of, I might say, the biggest recent success stories in the Serbian startup scene. It is a company that has managed to raise very strong funding rounds in a very concentrated and disciplined effort to try to revolutionize the chip design industry. So without further ado, Bogdan, thank you again for speaking to us, and the floor is yours. I think you're muted.
Sorry, I thought I could do it with a shortcut, but seems not. Thanks, Peter. Thanks for the introduction. Yeah, so as Peter said, I come from Anari. I'm a co-founder there and head of the R&D, so from the technical side. So this talk will be a bit more technical, but also because of the time, I'll just brush on some high-level things, some exciting things we're doing. So I hope after that I leave some space for questions. So just feel free to ask, and we can dig deeper in some details of what I show you. So Anari, as Peter told you, we are engaged in a broader ecosystem of communities. There is Wonderland AI Summit that we support. So it's a summit that once a year gathers many speakers from the AI field from whole world. There's Serbian AI Society. I don't need to talk about it. You already know. And there's CTAI also that is focused on that's forms communities around the world, also around AI. This is a slide regarding Wonderland AI Summit. So we have really speakers from all over the world, from big companies like Microsoft, NVIDIA, Huawei, Dell. And here's some of the people that have talked on Wonderland AI Summit. So you might recognize some names. So yeah, let's dig into technical things, which is my my field. So what we do at Anari, well, we ask ourselves two questions basically. So the first one is, what can hardware do for machine learning? As you already know, the progress of machine learning was in big sense led by advances in chip industry, so predominantly GPUs that have allowed long and very fast computations that are required for the training and also for the inference of the machine learning models. So we are continuing on that trend, and here is an example of what we are doing. So as Peter told you, we are trying to build a better way of designing hardware, and we're building tooling around that. So this is one example that we are trying to showcase. How can you be smarter about building hardware? So what's our example? Well, we've chosen to work in the field of 3D point cloud semantic segmentation problem. So you're probably aware of the semantic segmentation, but more usually more in the field of 2D images. But the same you can do with a 3D point clouds. So what you have a scanner that will scan some 3D area. It can be a room, it can be a building, it can be outside, like some spatial drone imaging. And what you would get, you will shoot like lasers from your equipment, and then you will gather the positions of points in your area that you're trying to scan. So, but what it doesn't tell you is what are those points, what do they belong to which objects. So here you can, here the field of semantic segmentation is working to make sense of this like sterile point clouds, and try to figure out what are the objects present in that scene that you scanned. So the product that we have built is called Thorax, and it's hardware accelerated machine. It's an inference engine that will speed up the semantic segmentation, but in the inference part, we're still using GPUs for the training. So it has there's a model that we engineered, and we built a tailored hardware solution that will accelerate that particular problem. I'll talk in a minute why we chose this problem and regarding the hardware acceleration. So the model, the architecture of the neural net is standard for segmentation. So you have an encoder part, which will try to get some smaller representation, so of the whole area you're scanning, and then from there it will try to recognize some features, and then decode that to basically extend those features to the original size, so you can identify objects in the original scan. So what does it look like? It's an example. So here are two images juxtaposed. So one, you have original 3D point cloud. This 3D point cloud is also colors. You can do that also. So we also you can shoot lasers, but in the same time you can take photos, and then you can combine the two to get colored 3D point cloud basically. So, and the other image shows the segmentation part, where you've detected some features of interest, and they're represented with different colors. So you can see the vegetation here in bright green. You can see some pavements with pink. You can see some low vegetation like grass and fields in green, and so on and so forth. So there are many cool things used in this architecture. So it's encoder decoder. There's also attention mechanisms. So they can be basically classified as a form of GNNs, which you will hear a lot about in this seminar. Yeah. So what's interesting about 3D point clouds that we wanted to explore here? Well, it's basically their graph-like nature. And what does that mean? It's that this data structure that you gather is pretty not uniform. And what should that mean in a processing thing? It means that you need to perform different operations in different scenarios. So with a convolution or 2D convolution, when you're applying it to 2D images, it's pretty predictable what you need to do with each pixel. So you have its neighboring area, you take it and you perform a bunch of multiplications and additions to calculate your filter output in one layer. But when you have 3D point clouds, you're not really sure what your neighbors really are. So every part of this scene is different. So there are more dense areas, there are less dense areas, and your computation cannot really flow in that easy and predictable manner as it can go with 2D images. So there's a reason why we said, okay, let's then build a custom accelerator which will be ready for these shifts in processing that needs to be done from one point to the other point. And basically what we achieved is currently four times efficiency against GPUs, because we're really tailored to this one particular problem. So what we are saying here with Anari is if you build the custom tailored accelerator for your specific problem, you can really achieve some speed ups and some cost savings when you're doing that way. So we are trying to, but of course, building hardware accelerators is not an easy task. We'll talk a bit later about that. So what Anari is trying to do is to facilitate that process and to bring tools that can help you with that. One important thing to say that our the products and the accelerators that are built with our tooling are deployed in the cloud, so it drastically reduces the number of steps you need to do if you want to work in this field. Because traditionally, what you would do, you would design your accelerator, and then you would send it to a factory, it's Taiwan, and then they will some months later you will obtain the physical chips that you design. But then you have chips, then what to do with them, you need to design some boards, you need to put it in some computers, so there are a lot of steps that we are basically mitigating by using cloud infrastructure. So this is just supportive slides so that they can see what we're talking about. These are just different architectures that the hardware can have that runs the AI. So to the left, you have a CPU architecture. It's most flexible. It can handle basically everything, but it has a limited number of parallel cores that you can execute, and so there are limited number of operations that you can perform in each instance. In the middle, you have GPU architecture that has been very successful with machine learning, and there you have many more cores, but it has its problems also. It has its limits. So it has 2,000, like see, 3,000 of CUDA cores that can operate in parallel. But contrast that with the FPGA. So FPGA is a programmable hardware that we program in the cloud, and that basically runs our accelerators. So with FPGAs, you have many more elements that can run in parallel, but they're much smaller, much less powerful, and then harder to engage. So that's where the whole tooling comes in. So, but we could also ask the reverse question. So what can machine learning do for hardware? So we're going to support machine learning with hardware, but then let's also use machine learning to help us with a process of designing accelerators. I talked about some of these steps. Here are listed some of the steps you need to do when you are designing hardware in traditional ways. You need to design your chip, you need to verify it, you need to integrate it with a broader input-output systems that you have there. Then you need to implement software for that. You need to send that to, as I said, to Taiwan. It's called a tape out. So they will basically bake your chips and send you back. So there are a lot of things you need to do in this process. So all of these steps, not all of them, but many of these steps can be automated using ML. So ML can help in a lot of these steps, and there are companies working at the various points in this chain to help bring ML to hardware. So for example, one problem is You can design your chip, your accelerator. You can design it in a logical way. So you're basically describing the functionality of the chip. So, but what needs to happen? You need to these calculations. So these processes that you described, these computations, need to be placed on a physical chip. So you need to say in which part of the chip, which computation will take place. So it's the same thing with CPUs. You need to say on which CPU core this process will run. But here you have like millions of places where you can engage, you can place your computation. So these tools are pretty they have pretty tough job of doing that. These tools are called placers, so they place your computation to physical chips, and they're called routers, so they connect, they route these blocks so that they can operate together. So these are really hard problems, and many companies are working that space also. But here in Anari, we are focused on chip design phase. So this number one here. So what does it mean to design a chip? It doesn't really differ from any other description of computation. So what you need to do is you need to specify the steps that your accelerator will do, as you have to do with any other software or any other computation platform. So but what's really different is that massive parallelism that you need to think about. So our brains, our cognitive processes are really sequential. So it's easiest for us to think in steps that are atomic. So you say, okay, I'll do this thing. Okay, wait, stop. Then do a second thing. Okay, what's what's the effect? And then it's easiest for our cognitive process to work like that. Even though our brains are massively parallel, but our cognitive process is sequential. So building like computation, describing computation in a sequence of steps, it's much easier to do. So traditionally, all software is described sequentially. You also hear it's called procedural design. So you just list the number of steps, but that is not really good way of describing parallelism. So here I just put out some paradigms that can help you describe parallelism, and different tooling and different platforms use different of these approaches for description. So the easiest maybe to grasp is this SIMD. It's short for single instruction, multiple data. So basically you have parallelism described at a scale of one instruction or maybe one function. So it's really like you are describing parallelism at a small step. So it's easier to grasp. This will be like I have 10 numbers to multiply in this one step. So I'll just say, okay, do it in parallel, but then, okay, get me back to my sequential world. The next thing, what you can do is what CUDA does and a lot of other, a lot of other procedures for engaging accelerators is the kernel-based approach, which is also single program multiple data approach. So what you would do, you don't limit yourself to a single instruction, but you say, hey, this is a function and a lot of things need to happen there. So but it's small. It's not on the scale of your whole computation, but it's something smaller, like convolution operation or something like that. So it's smaller at scale. And you say, okay, this computation needs to run for all of my data. So that's usually how CUDA works and GPUs work. that's a step a step up from the SIMD, but it's also limited. You need to also have these fixed steps that you need to work on. So, and you need to have the uniform data here. So it says a single program, multiple data. So you have a single thing that operates on multiple data points, and that's where GPUs are most powerful at. Even broader from that, you have BSP. It's basically where you synchronize your, it doesn't have to be single programs, so you can have multiple programs, but you have points of synchronization. It's called bulk synchronous processing. So you have a points of synchronization also, but now your workers can be of different varieties, so they can perform different things. This is usually used in distributed systems, in cloud, when you have like some microservice maybe architecture where you would engage a lot of services, but then you say, okay, now I need to stop and I need to see where I am. And so you have this synchronization points. So you basically have again sequence of steps, but the steps are larger and more heterogeneous. One thing you can do also, which is popular with web and cloud computing, like futures or promises or deferred computation. There are a lot of names for this. So basically, you are still writing your code in a sequential manner, but now some of the functions you are calling are basically spawned as a separate parallel workers that you can then sync later in your program. And the most powerful paradigm you can use is a message passing paradigm. So this is like anything goes. So you have a big graph of computing nodes, and you have messages that are delivered between those. Usually it's some form of data flow. So it has like a flow to it. So it looks a lot like it has small number of cycles, I would say. So it's like a directed computation graph. And you will have distributed nodes, and they would just, each of those nodes will perform some form of computation, and then it will send its result to the next node. So this is most powerful, but also hardest to work with, because it's least sequential of all those. And but with Anari, it's because it's most powerful. We are targeting that paradigm, but we are trying to make tools that will help you work with those. This is just an example to show you the process and how it looks like. So in the top part of this image, so this is basically a simulator that we developed, and so this is like you designed your computation, and now you want to see how does it perform. Is it functionally correct? Is it are timings okay? Can you do better? Can you squeeze more computation out of the system? So the top part of the image, you can see it's a graph. It's a computation graph. It's directed. You see that the flow of data is from left to right, and you have a lot of workers that are connected with interfaces with each other, and they are sending. So they are performing some work and sending the output to the next guy. And basically, you can describe any kind of computation like this. And so what we want to do with this, we want to later have an automatic system that will deploy our now message. So what you need to understand is all these workers are operating in parallel, which is another hard thing. So this is a graph which is like spatially hard to understand, but also below you can see the flow of time. So you have to think both regarding the space and time to really tame these beasts. So all of these workers are performing in parallel, and they're just working on different. So you can imagine a lot of data points coming from the left, and so they're performing in parallel, but each of them is working on different data points. So you could imagine this like a conveyor belt, like assembly line in a factory. So just so what do we want to do? What do we want to do here? You see that with a message passing, you're basically describing a graph that of components that communicate with each other. So what do we want to say? Okay, we have now graph neural nets. Let's try to make them help us with the reasoning about this graph. So there are a lot of questions you can ask. So are these two nodes that I connected, I as a designer, I connected few nodes, are they compatible? Are they as performant as they can be? Or do I have some other node, maybe some other computation unit that will go better here? Or you can ask really a lot of questions that are really hard to answer in traditional way. So what we started working on is using GNNs to describe these computation graphs and trying to teach them to extract knowledge that is useful for chip design. First of the things we're trying to work on is example where we want to ask the following question. So basically we have a cloud, and in cloud you have a large number of instances. So you have like CPU instances, you have GPUs, you have FPGAs, you have very heterogeneous pool of targets that you can run your computation on. So one question can be, okay, I have this graph and I have a number of workers. How would you distribute those workers on this heterogeneous devices and obtain maximum throughput or obtain minimal costs for your computation? So this is a work in progress that we are working on. We post this question in a form of the game. So we are using reinforcement learning here, and we are trying to make a system that will start from the simple graph you see here, the step 0, and then it will gradually build a graph. So add some components and also try to figure out where these components, where these workers should run on once they're deployed in the cloud. That is one example, but you can really ask lots and lots of questions. So we are looking forward to engaging from the various points there. So thank you for listening. I'm now open for questions if you want to dig deeper in some of these topics that I covered. Thank you.
Thank you very much for the great presentation, Bogdan. I'm sure that this area will get more and more exciting as time goes on. And I'm, of course, particularly excited that you're using GNNs combined with RL to solve some of these problems. Yes. We are, unfortunately, a little bit over time, which means we won't have enough time for live questions. But if you do have questions for Bogdan, please do ask them in Slack. And I see that there's already some questions in the Slack, and I'm told Bogdan will get back to them sometime later and answer them. So thanks so much for presenting Anari for all of us. I will now hand the baton over to Razvan, who will introduce our first keynote speaker of the day.
Thank you, Petar.